Here we'll go over the normal function of our neuromuscular junction. I've drawn that for you here. We have our motor neuron synapsing with the motor end plate, which is on the muscle. So we'll talk about a normal action potential and how that results in muscle contraction, and then how our depolarizing and non-depolarizing neuromuscular blockers interfere with that function. Let's draw our action potential coming down here in the form of intracellular depolarization. And eventually this will reach our nerve terminal where we have our voltage-gated calcium channels. So this will be step one, where our voltage-gated calcium channels then will allow calcium to flow inside the cell. So the action potential reaches our presynaptic nerve terminal and allows flow of calcium intracellularly. We need calcium in order to allow these neurotransmitter-containing vesicles to dock to the cellular membrane and then exocytose. So that's step two, where we have acetylcholine release. These vesicles in the motor neuron will contain acetylcholine, and they'll come and float into our synapse. That's step two. I've drawn an acetylcholine molecule for you here, so this is what that looks like. And then for step three, this molecule needs to bind to the acetylcholine receptor. And this is that receptor from the top-down view. There are two alpha subunits, and these ones are important because they have the binding site for the acetylcholine on them. So we need an acetylcholine molecule to bind each alpha subunit in order to change conformation of this receptor. So once we have both of these alpha subunits bound by acetylcholine, the receptor conformation will change and allow sodium to flow intracellularly and calcium to flow intracellularly, which causes a net local depolarization around where this receptor is. Now there's actually also potassium that flows out of the cell, and this would leave a negative charge behind intracellularly because we are letting a positively charged ion go out, but the overall net effect is depolarization, or a net positive charge inside from these ions flowing in. And that's our third step. So we'll call that acetylcholine binding and local depolarization. So just a net positive charge around where this receptor is. But this is not enough positive charge to depolarize the entire cell membrane. So next what has to happen is helping out from the voltage-gated sodium channels. So we can just show the same thing happen with this receptor that is closer to our sodium channel. We'll have calcium coming in and sodium coming in after acetylcholine binds to the two alpha subunits of this acetylcholine receptor, and there will be local depolarization that will spread to these voltage-gated sodium channels. So once this positive charge has spread to the voltage-gated sodium channels, it will allow large amounts of sodium to come in and propagate this depolarization elsewhere in the cell. So there will be multiple of these voltage-gated sodium channels that allow sodium through and help propagate this positive charge down our T-tubule. Let's draw another one here. Eventually this intracellular depolarization reaches our voltage-gated calcium channels. These are our dihydropyridine receptors, and they are in direct contact with the ryanodine receptors, which allow calcium to come out of the sarcoplasmic reticulum. So most of our intracellular calcium release will actually be from the sarcoplasmic reticulum when this receptor changes conformation. And that will be step 5, where we have voltage-gated calcium channels releasing calcium intracellularly. And this is calcium-dependent calcium release. This is also the problem site for malignant hyperthermia, where we have unregulated calcium coming out of the sarcoplasmic reticulum that cannot be shut off, leading to sustained muscle contraction. And we know the final step of this is the intracellular calcium causing muscle contraction. Now let's go over how our depolarizing neuromuscular blockers, i.e. succinylcholine, because it's the only one we use, will change how our neuromuscular junction works. Sux binds directly to the acetylcholine receptors. So direct binding to acetylcholine receptor. The succinylcholine molecules actually look a lot like acetylcholine. It's basically just two acetylcholine molecules mirrored. So two acetylcholine molecules bound by two additional methyl groups. So these are very good. The Sux molecules are very good at attaching themselves to the alpha subunits of our acetylcholine receptors. And what this causes is a prolonged depolarization. Normally what happens, let me just get rid of the Sux part of this so we know we're talking about acetylcholine. Acetylcholine will be broken down by acetylcholinesterase into acetic acid plus choline. This happens very quickly, so it takes about 1 millisecond before the acetylcholine is broken down in the synapse. Unfortunately, or fortunately, acetylcholinesterase does not work on our succinylcholine, so it will linger in this receptor. Let's add succinylcholine to this synapse now. So that's what these molecules are. They will easily bind to the receptors on the alpha subunits and cause the configurational change of this acetylcholine receptor. And it will allow lots of these ions to flow through, so lots of sodium and calcium to come through, as well as lots of potassium to leave. Instead of dissociating from these receptors very quickly and then being broken down by acetylcholinesterase in about a millisecond, they will stay here, or they'll unbind and then rebind because they're not being broken down. So this causes a sustained opening of these acetylcholine receptors. With that, we'll get a spread of this positive charge over to our voltage-gated sodium channels, which will also then let more sodium through, resulting in a sustained depolarization of the entire cell membrane, at least to a certain degree, and that's why we see fasciculations, which are uncoordinated muscle contractions as a result of giving succinylcholine. This depolarization of the cell will obviously spread to our calcium channels, and we will have calcium release. Only briefly, though. So our fasciculations are relatively short-lived. You may think that because succinylcholine is so good at binding these receptors, it causes the local depolarization, which spreads because of our sodium channels and ultimately releases calcium intracellularly, which would cause a sustained muscle contraction. But this does not happen for two different reasons. One of those being inactivation of these sodium channels. So after they've let a certain amount of sodium ions through, doesn't matter what the intracellular membrane potential is, they will actually stop allowing sodium ions to flow through the channel until the cell has properly repolarized and had time for this ion channel to recover. So even if there was a little bit of local depolarization around this sodium channel, it is effectively inactivated. So fails to transmit this negative charge to our voltage-gated calcium channel, so we don't get additional calcium release. So that's the first way, is inactivation of our sodium channels. And secondly, the acetylcholine receptors themselves will also be inactivated. So the succinylcholine binds and does indeed allow the sodium and calcium to flow in and potassium to flow out. But this will also stop occurring. So after sustained binding of the acetylcholine, so after a sustained binding of the sucs to these receptors, which doesn't usually happen with acetylcholine, this whole channel will actually inactivate itself. So we end up with flaccid paralysis, where there's just a period of brief depolarization and muscle contraction, which we see in the form of fasciculations, and then there's no muscle activity whatsoever. And at this point, you can say that you have effectively accomplished a non-competitive antagonism. Even if somehow we were able to release a whole bunch of acetylcholine here and try to flood these receptors with normal acetylcholine, they will have no effect. So if we're able to displace the sucs by adding lots of acetylcholine to this receptor, to this synapse, this still won't have any function because this acetylcholine receptor is temporarily inactivated, as well as our voltage-gated sodium channels are temporarily inactivated. So we can see that our depolarizing neuromuscular blockers have interfered with this step of acetylcholine binding to the acetylcholine receptor and local depolarization. And then it has also interfered with our voltage-gated sodium channel function. Now we'll talk about what happens with the non-depolarizing neuromuscular blockers. So rocuronium is one of these. Probably the one you're most likely to use, but there are others. These work all by competitive antagonism. So essentially they're fighting for a spot on the acetylcholine receptor to prevent your normal acetylcholine from functioning. Let's deliver ROC to this synapse now, so we'll make these orange. So the orange are the non-depolarizers. It will fight for a spot on these receptors with acetylcholine. And actually, you only need one of these alpha subunits to be bound by rocuronium rather than both, because you need both of these alpha subunits to be bound by a functional acetylcholine to end up changing conformation. So even if one of these alpha subunits is bound by the non-depolarizer, this will no longer function. So this is essentially enough, but we'll replace both of these with the non-depolarizer to show you that this definitely will not function anymore. So then we're not going to get the conformational change here, and we will not allow calcium or sodium to flow into this cell. So we do not get the local depolarization, and then certainly none of the propagation by the sodium channels. So clearly it is interfering with the acetylcholine binding to those acetylcholine receptors. But it functions in another way as well. So you'll see that I've drawn an acetylcholine receptor on the presynaptic membrane as well. So there are indeed receptors here. Normally, when acetylcholine is released into the synapse, it will also bind to these presynaptic receptors and bring calcium into the cell, which will help these other vesicles get ready to dock on the cell membrane. Without acetylcholine binding to these presynaptic receptors and readying these vesicles for release, we'll have less acetylcholine released anytime a action potential reaches our nerve terminal. So we need these presynaptic receptors to be bound by acetylcholine to ready these other vesicles for release. What happens with rocuronium then is, since it competes with acetylcholine for a spot to bind these presynaptic receptors, we will no longer have function of this receptor, and we will have less readying of these other vesicles for release. So we actually decrease the amount of acetylcholine that is released from the motor neuron when it receives an action potential. Let me just reinforce in red that ultimately the depolarizers also blocked our acetylcholine receptor, but also our sodium channel function. And then the non-depolarizers are interfering with the function of our postsynaptic acetylcholine receptor and our presynaptic acetylcholine receptor. Of course, the end result of both of these type of neuromuscular blockades is muscle relaxation, but they just achieve that by slightly different ways.